Okay, great. So our next talk will be given by Pengyong Ding from Penn State University, and he'll be speaking on a variance associated with the distribution of R3 of n in arithmetic progressions.
Okay. So I want to thank the organizers for giving me a chance to have a talk in a conference. And today I'm going to talk about the variance associated with the distribution of R0 of n in arithmetic progressions. So this question is a conjunction of two questions. The first question is about the function R0 of n, and the second question is about the variance associated with the distribution of a function in arithmetic progressions. So I want to start from the background of such two questions, and then I want to give some brief overview and some history, as well as the sketch of the proof. Okay, the first question is, what is the function R0 of n? R0 of n is defined as a number of ordered representations of n as the sum of three positive q's. For example, R0 of 1 and R0 of 2 equals 0 because there's no way to write 1 or 2 as the sum of three positive q's. Although we can write 1 as 1 cubed plus 0 cubed plus 0 cubed, and 0 is not positive, so it's unlikely to write them as the sum of three positive q's. And R0 of 3 is 1 because there's only one way, like 1 cubed plus 1 cubed plus 1 cubed. And R0 of 10 is 3 because we have 2 cubed plus 1 cubed plus 1 cubed equals 10. And there's a permutation. We can also write it as 1 cubed plus 2 cubed plus 1 cubed, or 1 cubed plus 1 cubed plus 2 cubed. So that's why R0 of 10 is 3. And we can also write the function R0 of n as a sum, as a formula, which is the sum of 1, such that s1 cubed plus s2 cubed plus s3 cubed equals n. And our understanding of the function is surprisingly poor. And recently, several results were proved by Robert Wang, and his paper is going to be published this year. And one of the results is that the sum of R0 of n, where n is less than or equal to x, equals gamma of 4 over 3 cubed times x minus the constant times x to the 2/3 plus an error term of x to the 5 over 9 times log x to the 1/3. And for the second moment sum of R0 of n, he only proved that the second moment sum is greater and greater than x, but it's less and less than x to the 7 over 6 times log s to the power of epsilon minus 5 over 2, where epsilon represents an arbitrary positive number. And there are several notes on the second moment sum. And in 1996, Hurley has shown that the second moment sum is less than x to 1 plus epsilon, then assuming that a certain L function satisfies the Riemann hypothesis. And it's conjectured that the second moment sum should be asymptotic to c times x for some constant c, but we only know that a lower bound of this order with a variable c larger than the obvious guess. In other words, if this is true, then the constant c might be quite large. And the second question is about the variance associated with the distribution of a real sequence in arithmetic progressions. And we consider V of S and Q, which is defined as the double sum of mod A of SQA minus F of QA times M of X, where A of S and QA is a sum of the real sequence under the when A is congruent to A mod Q, in other words, under the residual class of A mod Q. And the function f of QA and M of X approximately reflect the local and global properties of the real sequence. And if the real sequence A sub n is R3 of n, then we can prove that the local property f of Q and A is rho of Q and A over Q to the third, and M of X, the global property, is gamma of 4 over 3 cubed times X. And in this case, rho of Q and A denotes the number of solutions of the congruence L1 cubed plus L2 cubed plus L3 cubed is congruent to A mod Q. So that's the background of this question. So now let me give you the result. And assume that if epsilon is a positive number and delta is positive and less than 1/3, and if V of S and Q, then V of S and Q is Q times the second moment sum of R3 of n minus A1 times QX plus A2 times Q of Q to the 5/3 S to 1/3 plus an error term, which is named as U0 of S and Q. And A1 and A2 are all constant, but they are too complex. And if Q is greater than or equal to root x times log s, but less than or equal to x, then the error term is less than x to the power of 10 over 9 plus 2/3 times theta plus epsilon plus Q to the 2 minus delta x to the delta for some theta greater than or equal to 1 and less than or equal to 7 over 6. Or if we use the second moment sum, then U0 of S and Q, the error term should be less than x to the 10 over 9 plus epsilon times the second moment sum to the power of 2/3 plus Q to the 2 minus delta S to the delta. So this is the result. And now, in order to show you the schedule of the proof, I want to give you the history of such a problem. So the question on the variance associated with the distribution of a real sequence was introduced in work of Barben in 1966 in the special case that an equal to lambda of n, which is a one-Mangold function, which is defined as log n, which is defined as log p if n equals to a power of p, where p is a prime, and is 0 otherwise. And it's largely stimulated by developments in the method of large sig. And later, the special case was studied successfully by several different mathematicians, and among them, Montgomery established an asymptotic formula in the special case, and Hoory gave a simplified proof with a more refined result. And then Hoory developed the subject further by studying wide-reaching generalizations. And his method established that an asymptotic formula can be obtained for a wide class of AN, provided that if one has an asymptotic formula that A of SQA is asymptotic to X times F of Q and A, in other words, if the global property M of S equals to X, then we can find a reasonable error. Then we can find such asymptotic formula with a reasonable error term, and the main term is based on the second moment sum. And in the special case of the one-Mangold function lambda of n, further refinement occurs in Friedlander and Gaussen in 1996, and in Wang and Gaussen in 1997. The latter paper showed that some advantage could be occurred by applying a version of of a Hardy-Littlewood method. So in my proof, I have also used the Hardy-Littlewood method. And in order to use the method, we need to rewrite V as 2s1 minus 2s2 plus s3 plus the integer part of Q times the second moment sum of an, where we have s1 and s2 and s3 as follows. We need to use the Hardy-Littlewood method on s1. In other words, we can write s1 as an integral of u, an integral of f of alpha times mod g of alpha squared d alpha under the interval u, where u is a unit interval, in other words, an interval with less 1, and f of alpha is defined as a double sum of e of alpha q r, and g of alpha is defined as a sum of a sub n times e of n alpha. And the function e of x is defined as e to the power of 2 pi x, where I is the imaginary unit. So this is a Hardy-Littlewood method, and we can use the method to separate the unit interval into a major arc and a minor arc. So the major arc is, for the major arc, we'll get the main term, and for the minor arc, we'll get the error term. And having shown the usefulness of this method in that specific question, then in 1998, Robert Wang considered a more general problem. And he supposed that m of s equals x and f of q and a only depends on q and the greatest common divisor of q and a. And the real sequence satisfies the condition that the second moment sum is less than x. And we suppose further that a of s, q, and a is asymptotic to x times the local property f, which depends on q and the greatest common divisor of q and a, with a reasonable error term. And he got the conclusion that v of n q equals q times the second moment sum minus qx times the sum of the series g of q plus u of s and q, where u of s and q is the error term and g of q only depends on f. And notice that the von Mengel function lambda of n is not included in this special case because it's not included in this general case because lambda of n, the second moment sum of lambda of n is x times log x plus big O of x. So it's not less than x. However, in this general case, the property of the sequence a sub n is pretty well. So it's quite interesting to study the similar problem where the property of the sequence is not very well. An example of such a sequence or such a function whose mean value is a constant but whose mean square is unbounded is R of n, which is the number of ways to writing a positive integer n as the sum of two squares. This question was studied in the context of the above variance by Deng in 2002. And later, in 2012 and 2015, Ponsriam and Wang studied another problem, another function, which is d of n, the divisor function, which represents the number of divisors of n. And that function, the mean value of that function is also unbounded. And they got a result in 2012 and 2015. And in all of the special cases above, the behavior of the mean square is well understood. However, in my question, if the real sequence is given by R3 of n, then it doesn't satisfy the condition because as I have shown, the mean square of R3 of n is not known. So that makes the question even more difficult. Okay, so back to our question. After applying the Hardy-Littlewood method on S1, we have the main term, which is called S4, and it looks like this. And fq of beta is a function which depends on f of beta in the Hardy-Littlewood method. And recall that g of alpha is the sum of R3 of n times E of n alpha. So we can estimate S4 by S6 plus an error term. And actually there should be an S5. And in order to get S5, we need to replace this, the sum of mod g squared by q times t of q times mod of j of beta squared. And in order to get S6 from S5, we need to change the interval of integration from -1/2 to r 1 to 1/2 to r to -1/2 to 1/2. And we need to change the number of the sum from q less than or equal to s over r to q less than or equal to root x. And t of q entirely based on g, and this j of beta is based on and actually this j of beta doesn't depend on the function R3 of n at all. And in order to estimate S6, we need to evaluate such a function w of x given by the sum of h of l over l times s minus l squared, where h of l is defined from t of q. And the general way to calculate w of x is to use parent formula, use Cauchy's integral formula and the residual formula. And we need several L functions when using parent formula, including the zeta function. So that's how to get the result. And after getting the main result, we can see that if q is very close to x, if we say that q is asymptotic to x, then the exponent of x in the error term is 2. In other words, the error term will be pretty close to s squared, which is the same as the exponent in the main term. So we need to find more precise result in this case. So I have improved the result of v of n and q, where q is greater than x over k plus 1, but less than or equal to s over k. And in that case, we need to use another way to estimate S6 instead of using Cauchy's integral formula. And there are several examples, like when q is equal to x. And another example is that when q is greater than s over 3 but less than or equal to s over 2, or q is greater than s over 2 but less than or equal to x. And this is treated as a special case because it's also a special case in the paper of Wang and Gosson in 1997. And if you want more information, and if you want to find the proof of the results, please find them on the archive. And I have uploaded a preprint. And here is the website. Okay, thank you for listening to my talk.
Thank you.
Questions?
So
Preston?
I will ask a question if no one has that. Is anyone has a question? or I can ask one.
Go for it. I hear a child screaming. Maybe they have a question.
My son is behind. My son. Sorry.
No worries.
So so my question, so the VXQ is the discrepancy you're computing, right?
Yeah.
Okay, so I was just wondering, so in general, normally when you compute the Vinogradov type bound, a common technique a lot of mathematicians use is a linear dispersion method. So it's basically like you use some kind of Cauchy-Schwarz inequality, raise the power to the square, and when you have a modular square, then you use the fact a times a bar is modular square, right? So you multiply and you get a 3, you basically, when you multiply them, you get all the cross terms and you basically bound individually. Does it
Yeah.
make sense what I'm saying? Or
Yeah.
so I mean, like, is that like did you try, or normally in this kind of problem you cannot use linear dispersion method?
Basically, I think that I didn't try to use other method for such questions, but for the Hardy-Littlewood method, it's mainly based on so it's mainly, I mean, to rewrite the sum of the difference as like a squared minus 2a times fm plus f squared m squared in order to get.
Then so then you bound each of them S1, S2, and S3.
Yeah.
Oh, I see. Yeah. Okay. I mean, yeah. Thanks.
So I have a question. So you stated the theorem. I think it was maybe due to Vaughan, where there were lower order main terms in the asymptotic. Could you show that again, please?
That one, or is it the main theorem, right?
There was something with yeah. So when doing and I think there was one more as well, but doing the circle method, where do these lower order terms show up from?
The lower order terms like this one, or
yeah, well, it looks like you've got, I guess, 3 distinct main terms there.
Yeah, there are 3 main terms.
Okay, so yeah, I guess so. I'm not an expert in the circle method, but all the applications I've seen, you get like one main term, and then like some error term. So where are multiple terms coming from?
Actually, there should be at least 2 main terms. The first main term is q times the second moment sum, and the second main term is in this question given by Wang, the second main term is given by calculating SO6. So SO6, and but in my question is both the second term and the third term are given by evaluating as S6. So that's why. So
okay. Could you show me S6 again? Sorry, I forget which it was.
Yeah, this is S6. So we need to evaluate something like this. And
I think also after he's splitting up S1, S2, S3, then splitting up more, then you are trying to using the circle method there. So that's why you're getting main term from each of the top. I think that's what happened. I understand. So he's getting in the beginning S1, S2, S3 by breaking the square.
Yeah.
He's still using circle method there. Maybe that's why you're getting, but as Frank said, you are getting probably main term from each of them. That's why you're getting multiple main terms or lower order main terms.
Yeah, actually the main so actually after having after using the Hardy-Littlewood method on S1 for S2 and S3, I just rewrote them as -2 times S2 minus S3, which is the error term, and there's another S3 as the main term. So you can combine the main term S3 with the main term 2S1. So yeah, so that's how to get the result.
Okay, great. Thank you. Any further questions?
Yeah, may I ask a question?
Yeah, so we got 3 minutes, so probably keep it short, but yes, go, please.
So is it too hard to compute the moments? Because if you know all the moments, for example, you can get the variance.
Yes. Yeah.
I not know how hard it is. So
Yeah, there are several ways to to evaluate the second moment. Some, but it's so.
because the generating
That's the
function
best
of
result.
which, if I remember, I think it's theta, right? So
That one.
maybe we can discuss later.
Yeah, but anyway, that's the best result that we have found. So, yeah.
Okay, let's thank our speaker again.
Thank you.
All right, so I guess we have just 1 minute, and so we have parallel sessions again, and in this room, Cesar Lupu. Did I say your name correctly?